Alright, so we are in week 14, and week 14 is pretty much the main thing that I want to tell you for this class, which is graphs. And graphs are a very unique data structure. One of the few that, well, the one data structure that you could use to display something that is on a map, right? So in this particular case, if you have maybe a map of cities and they're all connected to each other in a certain way, then you could create you can create this relationship in your program using adjacency matrices and vertices and vertex arrays, for example. So that's one of the main applications of graphs. They're regular line graphs that you have seen in math. You have your x and y axis. You can have weighted graphs where the distances between different vertices has a specific value, right? You can also have directed graphs where there's maybe one or different possible directions. For example, there's a way from San Francisco to New York and from New York to San Francisco, but there's only a way from San Francisco to Albuquerque and only a way from Albuquerque to New York, right? So there's some unique relationships that may be needed for a map representation that can be saved in your program and analyzed. Some of these analytics, for example, would be trying to, let's say this here, the map graph that you have on top, this could be some kind of a maze, right? You're inside of a maze and you're trying to find your way out of a maze, which is very similar to how different decisions affect outcomes in a gameplay, right? If you make a certain move, then certain different things that are possible to happen. For example, if you're playing the game of tic-tac-toe and you hit one of the little squares, then there are 8 different possible ways for the next move to be made. And the one after that, after you click the 2 of them, then there's 7 possible ways for a move to be made. So these decision makings can be simulated in a graph. And a graph is basically a general type of tree, right? So remember trees are types of graphs, right? A heap could also be said that is a type of graph. Okay, so your binary search tree is a special kind of a graph, right? And the heap is a special kind of a graph. So the graph is the broader category. But it is similar to a binary tree in that there is nodes or vertices which are connected by edges, right? But there could be multiple different paths from one node to another node, right? What made a tree was that if you're trying to go from one point to another point, there's only one possible way. From root to a node, there's only one possible way to get there. But there's multiple ways that you can get from one place to another place in a graph, right? So if I'm trying to go from I to just to F, I can go from I to J, then E to F, or I can go from I to J and F, right? G and J, right? Or I can go through the H and then the B and the A and then go to the F. So there's multiple paths. Other than figuring out the possible choices that maybe one decision can influence many other ones, another application of graphs is trying to find the shortened distance between two places in a map, right? So what is the shortest path for me to take from letter I to letter F? Well, just by eyeballing it, you're going to go through the G and then you're going to get to the F, right? But there's other possible paths. You can go through J and then E and F, or you can go through the H and B and A and then go to the F. So determining the shortest path is another possible application. And this comes into play when we're talking about the internet, right? The internet is just, imagine this right here is your internet. It's just a collection of routers, right? And how does your packet or pieces of information know how to go from one part of the internet to the other part of the internet? Well, each of these routers, they have tables in them that keep information about like how long did it take to go from this place to this other place, right? All that information can be analyzed with the graph, and you can figure out the shortest possible path from one place to another place. Okay, so those are some things that we can do with graphs, and let's have a
So finding the distance between city to city would definitely be a weighted graph, where it would specify the distance on the edges?
It does not have to be a weighted graph. I mean, we could assume, for example, that all edges are of equal distance, right? So let's say that, suppose for simplification, the way we could eliminate a weighted graph, it would be a weighted graph if it's a real life situation, yes. But for simplicity's sake, we could say that, okay, well, on this map, all of these different paths are the same, and then we can analyze it that way. Just basically, we can start by analyzing how many paths or how many separate paths it took to get to one place, and yes, you can also look at the value of each of these paths also. But the weighted graph is something a little bit more complicated, so I'm going to introduce you to the basic graphs. Okay, and I mentioned to you graphs last time we were here. I think maybe not, and I did, right? Yeah, right. But I'll tell you a little bit more of it. So a little bit of applications, and then I'll get back right into it. So see what I have in here. And again, it's from the book. It's from the LaFour data structures, and also there's the Carano data structures as well. I'll pretty much let you read through it. Just so you know, it has a background in mathematics. This mathematician Euler started using this idea of graphs when he was trying to figure out there was like a series of bridges, and what city it was I can't remember, in some place in Poland, and he tried to figure out is there a way for you to cross all the bridges without repeating crossing one of these bridges more than once, and that was like one of the famous problems, and he actually proved that there's no way to do that. All right, so it has a long background. A lot of these things that we're using, they come from math. There are mathematical models. So in here, why don't I go back to my little example that I had for the CSIS27 class, so that I can show you a little bit easier example. All right. And I have a couple of videos for that class with a little more detail. So I highly recommend you take the Java data structures, because we can go a little more depth in there. All right. So first of all, I remember that I told you that we're going to create some kind of a relationship. So let's say, for example, this is my picture, and that's a type of graph, right? We can call it a graph. It's more like a tree, but whatever, it's a graph. Okay. So what we're going to do here is, first, based on this here, we're going to create some kind of a relationship matrix, right? So the way we're going to do the relationship matrix, and again, this is the part that comes from math, is we're going to arrange these things. So the letters are going to be your labels for the columns and the labels for the rows, like so. Right? And every time, let's say, we're going to look at, if we're at the row that is A, right? If we're looking at row A, that means now we're looking at what connections are made with A, right? Well, B, C, D, and E are connected, so those are the ones we mark with ones. All the other ones are zeros, right? A does not have any connection with F, G, H, and I. Same thing, if we go to B, what are the possible connections with B? Well, it's connected to A, and it's also connected to F, and that's it, right? Everything else is zeros. So using this adjacency matrix, we can save the relationships that come from some kind of a visual map into our program. Okay? And now that we do this, then there's the possible ways that we can traverse this maze or graph or whatever you want to call it. Okay, so the first one is the depth first search, and that was the one that's used for, you know, trying to figure out possible outcomes in a game, for example. Another illustration for the depth first search is, you know, being in a maze and having a string, right? I gave you that example last time. Okay. So the way this is going to be implemented is it's going to be done using stacks, right? So the way this is going to be done is we're going to visit one of these vertices, and we're going to put it on the stack, and then eventually we're going to remove things from the stack. And the rules are this. Okay, if it is possible, visit the adjacent unvisited vertex, mark it, and push it on the stack. And if you can't follow rule 1, then pop the vertex off the stack. Okay, so basically we're starting at A, we're going to try to visit B, C, D, and E. We visit all of these that are connected to A, we're going to put them all on a stack. Okay, and once we put that, actually, sorry, my bad, I'm thinking breadth first search. We're trying to get as far away from the A, right? So we're going to go A, then we're going to visit B, and then the next thing that is unvisited from B, which is the F, and the next thing which is unvisited from there, which is the H, and we put these on the stacks one by one. Okay? So once we can't follow rule 1 anymore, right? There's nothing else to connect from H, then we start removing things from the stack, right? So we're going to remove the H from the stack, then we're going to remove the F from the stack, we're going to remove the B from the stack, and then we're back to the A, right? And now we're going to try to follow C. So we're going to put C on the stack, right? C goes on the stack, and we're going to try to go further away. There's nothing in there, so then we're going to remove the C from the stack, go back to the A. Next place is D, try to get as far away on the D path as possible, and then we're going to add the D, G, and I on the stack, right? And then when we get to the I, we start removing it, going back to the A, right? So that is the way that this thing works. And again, I'm going to show you a Java code for this because it's easier. All right. First of all, you need to break this down into like smaller, easier to understand pieces. And one of these pieces is how do you get the next adjacent unvisited vertex. Okay. So this thing is going to do just that. We're going to basically start. We're going to look at starting at one of these letters. We're going to try to find what other one is next to it that hasn't been visited. That's basically what it is, right? So we're going to, with this thing here, we're going to look at what letter, if we're starting at A, which ones are connected to A. That's the first piece, right? So the adjacency matrix shows 1 when there's a connection, and the second piece here tells it if we haven't visited it. Okay? So basically, if we look at this picture again, right, we're trying to visit B, C, D, and E. All of these are going to be 1 because they're connected to A. And then initially, they're all not visited, but first we're going to visit this one, we're going to mark it as visited, then we're going to visit this one, mark it as visited, and et cetera, et cetera, et cetera. That's how it's going to work, or whatever sequence that we're going to visit, right? So first we're going to visit the B, then the F, then the H. Okay, so we go in there, and let's have a look at first of all, what is my graph, right? So I'm going to start with some smaller, simpler picture. This is my graph, right? So there's a connections with when the A is connected to B and D, right? That's these. Then B is connected to C and A, right? B is connected to A and C, and then et cetera, et cetera. So first I create my adjacency matrix. The way I do the adjacency matrix is using, where is the main? There's the main, right? So this is my main. And in the main, I'm going to create a new graph. What is the graph? Well, the graph is this right here. Okay, and inside of the graph class, you can also have your stack class, and the stack is going to be just the exact stack that you have written already. Okay, so initially, when we create a new graph, we tell it that we're going to make an array of vertex lists. Right, vertex list is basically this here. Right, so it contains the letter for each of the vertices, and it also contains a Boolean true or false. Right. I don't know where that is. It is right here. Yeah, so this is your vertex, right? So every vertex has a character label, and it has a boolean to mark whether it was visited or not. Okay? So we make an array of these things, right? Give each of them a letter, and then the next step is we're going to create the relationship between these different letters. And since this is the picture we want, then we use the add edge method or function, whatever you want to call it, which is this thing right here, right? So in order for me to tell it, okay, mark this and this, the red ones, right? What am I going to tell it? I'm telling it put a 0, right? Put a 0 and a 1 as an index, right? So 0 and 1 goes here. You're going to have a 0, 1, 1, 0, and that basically creates this relationship, or puts the ones in here. And then we do similar thing for the other ones, right? Just based on the picture that we have. And we have the adjacency matrix for this thing set up. The next thing is my depth first search algorithm, which is right here. Okay? So what is this thing going to do? Well, first we're going to start at the first index, and in this particular case, we're starting at the letter A, right? So initially we're going at vertex list 0. Vertex list 0 is your A, right? So we're at the A. We're going to mark that thing as visited, right? We're going to change it to visited, which is this piece. Then we're going to display that thing. What is the display? Well, it's this little function right here, which just shows you, the letter A. And then we're going to push that thing on the stack. All right, so it's helpful to have like a separate place where you can keep track of what's in the stack. So what did I put? I put 0 on the stack, right? So if this is my stack, I put a 0. What is the 0? 0 is the index of my vertex list. So I'm basically telling it store the letter A in there. Not really the letter, but how I can refer to it. Okay, so that's in my stack. Then I'm going to go inside my while loop and try to go through, as far deep as possible. Okay, so the first thing I do is I say v is equal to the get adjacent and visited vertex the stack peak. Right, the stack peak is going to do what? It's going to give me this letter A. All right, so I'm going to get I'm going to get this index 0. Right, that's what it's going to return. It's going to return the 0. So then I do get adjacency ADJ unvisited vertex 0. Right, that's this step right here. Okay, so what I'm actually telling it to do is, if this is my V, right, V could be pretty much thought of as the number of your row, okay, in this adjacency matrix. So I'm telling it, look at V is equal to 0, which is telling it, look at this row, right? In other words, I am at the letter A right here, and then I'm going to try to see where letter A is connected, right? We're not going to say it's connected to itself, but it's connected to B because there's a 1 in there. That's where this thing is true, right? So the ADJ matrix of 0, 1, right? J is equal to 1 when this thing is equal to 1, right? Is equal to 1. And then vertex list J dot visited is equal to false. What is J in this case? J is 1. So vertex list 1 is false. So perfect. We haven't visited it and it is equal to 1. So now we're going to bring back the index where this thing was found. And where was it found? At J is equal to 1. Okay, so then we return the 1 back in here. V is equal to 1. Alright, so then that means now V here is 1. It's not equal to -1, so we're not going to do the if. We're going to go into the else. We're going to mark this thing as true, that it's visited. So now this becomes true, right? This one here. Then we're going to show it, right? We're going to show the B. We're at the B now. And we're going to push it on the stack. So now we're pushing the index of B, which is the 1 that we got from here, on the stack. So there's a 1. Okay? So at the end of this, we showed the B. We have a stack of this. And we change this thing to visited. Okay? Then we go back and we do it again. Alright? So now the next thing we're going to do is we're going to peek, right, from the stack. And the stack from before is a 1, right? So I get my top value from the stack, which is the 1. and I'm going to call this function here the get ADJ unvisited vertex with 1. All right, so I send the 1, which means that I'm looking at this particular row. All right, the first thing that I'm going to look at is if B was visited. Well, B was this one, right? B is already visited from before, so this one here doesn't matter, right? Because it was already, because this piece here is not false, it's true, right? So B of 0 is true, B of 1 is true. So the only thing that we need to consider at this point is from the 2 and after, right? So if we look at this one, that is my J of 2, which means that vertex list J of 2 is false. That's good. And it is equal to 1. So this piece, all right, ADJ VJ is, that's what? That's my row 1 and J2, right? So then we're going to return the 2 because that's the value of J. We bring it back. V is equal to 2, all right? This first if is not going to happen. We're going to go into the else, right? We're going to mark this thing as visited. So now these 3 different things have been visited now. The A, B, and the C have been visited. We're going to show the C, the display vertex, and then we're going to push the C on the stack, which is the index 2 that we got from here. Okay, so now this is the stack after. Next thing is we're going to attempt to now go further down in C, right? So we're going to peek. We're going to get C from the array, from the stack here, right? So we're going to get the index of the C in here. And we're going to do get ADJ unvisited vertex of 2, right? 2, because this is the 2, right? So I'm sending that 2 in there. All right, so V now is 2, which means I'm looking at this row, right? So I already looked at that row, by the way, right? Did I? No, I didn't. This is the first time I'm looking at this row. Okay, so I'm looking at row is equal to 2, right? And first of all, the B has already been visited, right? So the B was this one, right? That's already been visited. The C has also been visited already. So basically these first 3 ones don't even count, right? Because see here, 0, 1, and 2, they're all true. That means that 0, 1, and 2, which are basically these here, we don't even need to look at them since they're true from before. That means we only need to look at these last 2. And these last 2, this adjacency matrix is not equal to 1 for those. So that means I didn't find anything, right? None of these have been unvisited and equal to 1. So at that point, the loop ends, and then I'm going to return a -1, right? So now I get a -1. If I get a -1, I'm going to pop the thing from the stack. So it looks like it goes from here to here. Okay? All right, so we got rid of the top thing in the stack. Then we're going to do the same thing again. We're going to go in there. We're going to try to look at the top thing, look at the stack, right? We're going to do a peek here. We're going to get the 1. We're going to set the 1 over. We're going to look at this row here, and it's going to be the same deal. Look at these first 3. This one, and this one are basically these 3 values here, and whenever you have vertex list of 0, 1, 2, they're true, so we don't even need to look at these 3. We only look at the last 2, and we already see that they're zeros, so nothing to be found. Returns a -1, right? If it gets a -1, then we're going to pop the thing off the stack. So now the stack changes from what you see in here, right, to what you see in here. So we're only left with the 0 in the stack, and the 0 is the index of the letter A. Okay? So now, again, we're going to look at the stack, and we're going to do a peek. We're going to get this number. We're going to send it over into our function, the get adjacency unvisited vertex, right? So now we're telling it send a V of 0. V0 means we're going to look at this row, right? And again, like before, it's the same situation. The first 3 are true, so we don't even care about them. This one, this one, this one, right? We're going to look at the one after it. This one here is false, which is good, and it is equal to 1, right? According to this little thing that I have in here, right? So ADJ of 0, 3 is equal to 1, right? 0, 3. So that means that I'm going to return the J of 3, right? Return 3. V is equal to 3, right? Which is not equal to 1. And then we're going to go into the else. And we're going to do, I messed this up. This has to be a 3. There you go. right? So then we're going to mark the third one as true. So now these all have been marked as true, okay? We're going to show the D, right? And then we're going to push it on the stack, all right? And then next thing is so on and so on and so on. So basically you just have to follow this train of thought, and you're going to go to the E, right? When you get to the E, you can't go any further, and then you're going to pop from the stack. And when the stack is all the way empty, you can't go any further from the A, then you're done, and then you just make all of your flags equal to visited, to false. So basically mark them all to unvisited so that you can resume this process. Okay, that's the depth first search. There's a breadth first search. Okay, so the breadth first search is, here's the same. You already know how to make the relationship matrix. The way we're going to do this one is, I like the explanation of like a ripple effect, right? So if you drop like a stone or something in water, it creates ripples, and these ripples start expanding further and further and further. That is how the breadth search first works, right? And what this can be used for is you can use it to determine basically the first time a ripple hits something, that's the shortest distance between the origin and that something, right? So if you're trying to find you say I'm trying to find the shortest distance between F and G, right? Well, you start a depth first searching algorithm at F and start creating these ripples, and as soon as your ripple gets to G, however many paths you went to get to that is the shortest possible path, right? And if we're going to be doing a depth first search from F, we're going to have to go basically B, and then we're going to try also H, and then we're going to try to also go from F to A, then we're going to go from F to I, and then eventually we're going to figure out, oh wait, this path here is a little bit shorter. I can go from F, I can go H, I, G, and then as soon as I hit the G, that's the shortest path. And that's how the breadth first search is going to work. Okay, so in this case, the breadth first search starts at A, right? We're going to visit the B, C, D, and E first, and what we're going to do is we're going to use a queue to put them all in a queue as we visit them, right? So the rules are this. You're going to visit an unvisited vertex adjacent to A, right? And if you basically keep doing this until you visit all of them that are adjacent. The rule 2 is if you cannot do rule 1, right, what you're going to do is, by the way, these are going to get put on a queue, right? So this is my queue. As soon as I visit, so I'm starting at A, right? So that means I'm going to visit B, C, D, and E, which are what I put in my queue right here, right? So B, C, D, and E are on my queue. I cannot visit anything else after, right? So I visit all of them. Then I'm going to pop the first thing or remove the first thing from the queue. So the B leaves the queue, and I'm left with a queue of C, D, and E, right? B becomes the current index, right? Basically same with the A used to be before. And then I'm going to try to visit every index or every vertex that is connected to B, right? So the only thing that's connected to B and not visited is F. I visit that thing. I can't visit anything else. And then, right, so C, D, and F. And then the next thing I'm going to do is I'm going to remove the C from the front of the queue. And now C becomes my current index or my current vertex. Can I visit anything from C? No. So then the next thing I do is then I'm going to remove the next thing from the queue, which is the D. So I remove the D from the front of the queue, and now D becomes my current vertex, right? And I'm going to try to go as far, I'm going to try to visit a vertex that is adjacent to D and it has not been visited, which is the G. I visit that. That's why this thing goes on the queue that I have in here, and so on and so on and so on. Okay, so that's how it works. You're going to add and remove things from a queue in this manner. And when the queue is all the way empty, you're done with trying to search with the breadth first search. Okay, this is your entire breadth first search in Java, which is again very similar to C++. Just ignore the public, and it's pretty much the same thing. So syntax is nearly identical. Okay, so there's also private and public are kind of just ignore them for now. you can look at them when you take the class. So I have the queue in there, right, which is just the good old regular queue that you had to write, just a few lines of code. And again, what is a queue? Well, it's a line of people, right? People come at one end, leave at the other, and it's all done using an array and limiting the user on how they can add and remove from that array. This is your vertex, same as before from the previous depth first search. There's your graph, right? And how we make the relationship matrix. I'm using the same little picture that I had before. Same way to make the relationships in the main. Now, the only thing that's going to be different, well, the main thing that's going to be different is we're going to be using the breadth first search, right? And by the way, you can put both of these into one program, breadth first search, depth first search, and, no problem. So the breadth first search, right, works with two separate loops, right? So there's one loop in here and there's another loop in there. The inner loop, you can think of the inner loop as the one that is going to create these ripples, right? So the inner loop is the one that's going to make these ripples spread to all the adjacency vertices, right? So if I am at the letter A, right? If I'm at the letter A, well, I'll show you in a minute, okay? But the inner loop is the actual ripple effect. Okay, so let's look at how it works. So initially, I'm going to mark this vertex as visited. I'm going to display this vertex, right? Show the A. And then I'm going to insert it in the queue, right? And I have the queue in there just so you can remember. There's my insert. So initially the queue starts as this, which is front is equal to 0, right? Based on my constructor. Rear is equal to -1, right? That's what it is from before. Then I start inserting, right? So I insert a J. What is J? J is 0, right? J is the index of A, right? So I'm going to insert it in the queue. I'm going to move my rear to +1. So rear is 0, and this is the beginning of my queue with the only thing in the queue, which is 0. Okay? Now, that's it. So the next thing I'm going to do is I'm just going to I just break it down. Now I'm going to emphasize on the loops, right? I have already done this part. I'm going to focus on the one under it. All right? So the one under it is the loop. So we go in the loop, and the first thing we're going to do is we're going to say V1 is equal to the queue remove, right? What is the remove? Well, it basically moves the front, right? The front moves forward, and we grab whatever was in the previous front, so which is this. So we grab the 0, put it in temp, right, here, and then you move the front. And we're not even going to deal with wraparound issue. Imagine this queue is big enough, right? Don't worry, don't even worry about the wraparound. Imagine this queue is like 1,000 long. Okay, we haven't got to the end at all. So then I'm gonna grab this V1 and I'm going to feed it into my get adjacency unvisited vertex function, which is here. So I'm putting the 0 in there. Okay, and now what we're telling it is we're gonna look at the row, right? Row 0, just like we did from before. For V0, we're going to try to find the first one that's unvisited, which is this one right here, and we're going to return the index of that, right? Just like we did with the previous one. Okay, we get that thing, we'll return the 1, right? Then we're going to mark it as visited, right? So this thing now is visited. We're going to show it, and the next one is we're going to insert it into a queue, and that means that my queue is going to change from this to this, right? So what happened? I moved the rear. Okay, so whenever you add somebody, the rear moves. Whenever you remove somebody, the front moves, right? So now I've moved the rear from 0 to 1, right? So there's basically just one thing in my queue. That's why the front and the rear are equal to that thing. All right, so that's it. And then we go through the loop again, and since this thing is not equal to 1, right? It wasn't, well, basically, let's see. So we're going to go with a 0 again, right? So 0, V, get adjacency in unvisited vertex of 0. So that means that we're still staying in this row, right? We examined that row before. We found this thing. Now we're going to the next one, and we're finding this one, right? But notice what we're doing. We're staying on the same row. Right? So that means that this loop here, see this inner loop, That's the one that I'm telling you that it creates the ripple effect, because notice that we're basically finishing, we're going to check everything on row 1 until there's no more connections. And what does that mean? Basically, you're telling it, you're at A, now look at everything that's next to it first, right? So that's the ripple, basically. Okay, so we're going and we're visiting the B and the D first, and then that's the inner loop. Okay, so this time we're going to find an index of 3, right? That's where this J is going to be equal to 3. That's what we're going to return here, right? So that means the V2 is 3. What is the V2 3? V2 equals 3 is this right here, right? So index of 3 is the D. We're going to show the D. We're going to mark it as visited, and we're going to insert in the queue. So now my queue contains a 3 right here. So the rear moved again. Okay? So we're inserted the index of the letter D in my queue. Then I go and do this again. I'm still at the 0, right? We're still trying to go through this loop, the inner loop in here. Okay? So still trying at the 0, but there's nothing else left in the 0 in row 0. Right? So they have been already visited. There's nothing else unvisited. So we return a -1. When we return a -1, this loop stops. And then the next thing we're going to do is we're going to remove from the queue. Okay? So the queue, which used to be this, right? This is basically your queue. We're going to remove from that queue so that it becomes this. Okay? So what happens? We're just moving the front. Okay, we're going to store the temp. We're going to get the 1. We're going to store it in variable 1. In variable temp, and we're going to move the front here. Okay, so basically, just think of it as there's only one thing in the queue, which is this 3. Okay. Anyway, so we got the 1, right? Which was this when we did the queue remove. We got the 1. That's why this V1 is equal to 1. Then we're going to put a V2 is equal to get the adjacency unvisited vertex 1. Okay? The next adjacent unvisited vertex of 1. Now we're looking at this here. Right? And we already know that J of 0 was visited. Right? Because we already visited the A. We already visited the B. Right? We actually also visited the C, the D. Right? So all these are visited. So the one that wasn't visited is a 2. Right? Which is this. And it is also equal to 1. So we're going to return J of 2, right? Come back here, J of 2, mark that thing as visited now, show it, which is the letter C, insert it in the queue. It looks like this, right? So this is your front, this is your rear of the queue. Again, at this point, letter C. I don't know why we're removing. No, we're still doing this. So I don't think. I don't know why we're in here. I think I might have messed it up because. Are you noticing something? I'm still supposed to be in this loop in the C, right?
Yes, because you're checking for like all the...
Exactly, so I skipped a step. Alright, so basically what it is though, at C there's no more left, so then it's going to return a -1, and then when it returns a -1, yeah, so I skipped a step. Got it? There's a missing step in here. Basically, we're going to have to go through the C one more time. We're going to see that the C, right? So once we find the C, right? We find the C. We're going to show it. We're going to try to go through the loop one more time. The first thing is to do this get ADJ unvisited vertex of 1, right? So since we already visited the C, then this thing is going to return a -1. When it returns a -1, then this loop stops, and when that happens is when this thing is going to happen now, right? So that's the step that's missing. So now the next thing is, after we couldn't find anything else on C, or after we could not find anything on this row for B, then we're going to go and we're going to remove, okay? And what are we going to remove? Well, it used to be this, right? And now when we remove, we're going to move the front forward. We're going to make temp equal to this value, and we're going to return it. So now V is going to equal to 3. Okay? So now that V is equal to 3, we're actually looking at this particular row, right? These other ones have already been visited, or they're equal to 0. The only one that's left is the 1. So we're going to return a J of 4, right? Returning a J of 4. So now we're going to show the E. Okay? So and what's the order in which we show this? We have a C, then we have an E. Is that what we want? Yeah, we wanted to show the C, and then we want to show the E. So these are the two that are equally distanced from the letter A, right? And before that, we had a B and a D. Okay? So anyway, I showed the E, and I marked it as true, right? And then I inserted it in my queue. So this is my letter E basically in the queue, okay? And at this point, everything is visited. So what's going to happen now? This loop right here is going to keep going and going and going, and it's only going to be returning negative ones, because it can't find anything, right? Which means that this other loop here now is going to keep removing and removing and removing from the queue until the queue is finally empty, and once it's empty, your job is done. Okay? And just one more thing to show you. Yeah, I know I threw like a lot of stuff at you today, but not that. No, not that either. Let me show you. This is one of the students in the Java class wrote this. I'll show it to you. All right. So this is, she was asking me like, what's an actual application of this depth first search algorithm? And I told her like you can find a node if you're given a node. Not the depth first search, but the breadth first search. Given a specific node, you can find the distance between another node, right? So what does she do? This is pretty much your code for the breadth first search algorithm, right? What did she do? She added the indexes of what node you're starting and what node you're ending, right? Since we know that letter A is index 0 and letter B is index 1 or whatever, right? Those are these two numbers, where you start, where you end. This display piece here is just so that you can, if this is true, then you're going to be showing this, right? You're going to be showing what you just saw basically, right? So this is the exact code of the breadth first search algorithm, except she added an if in here and she added an if in there. So in other words, she only wants it shown if this thing is true. Otherwise, what this thing is going to do is, again, it's the same exact code. The only thing she added was this piece right here. And that allows you to basically store the distance of all the different vertices into an array of distances. Okay? And then you can show that particular distance, which is calculated and found using this. Okay? So it's actually a pretty clever implementation. There's a lot of other algorithms out there that deal with this. But it's just to show you that once you understand how the breadth first search algorithm works, you can throw it in very useful applications. Okay? Any questions? I might want to redraw like some information on how this thing works out, but this could be something that's actually useful to do. Since I walked you through all this other stuff, try to walk yourself through this and see how it keeps track of distances and how distances are stored, because believe it or not, in a lot of job interviews, you're going to be asked this question right here. They're going to tell you, find the shortest path between two whatever, right? And the code to do this is not a very long one. As long as you understand how it works, it's literally like what, 10 lines of code, 12 lines of code. So yeah.
Can you post that?
Yeah, well, it's in the.
It's already there?
I don't want to post her program, but this you can look at the video and you can type this up to get your own breadth first search. Everything else is the same.
Okay.
So yeah, just type her code to see how it works, and then trace it out on Excel to see how, you know, how these different numbers change. Okay. Yeah, so it basically stores what it does is it goes in there and it calculates the distances for every one of these different nodes in the graph, right?
So are these nodes in her calculations equidistant?
Yeah, we're assuming same distance. Yeah, we're not factoring in weight. Yeah, we're just counting how if these paths are the same length, right? But you could do similar. You can apply this to weighted graphs as well. Right, you just have to factor in the weight. So that's that's an interesting application. I was actually really impressed she wrote this because it's not easy. Okay, so if you try to understand it and you understand it, you're ready for one of these big job interviews that they're going to be, you know, questions that they're going to be throwing at you most likely. Okay, so what are some of the complicated questions they can throw at you? This kind of stuff. Okay. So know your breadth first search, know your depth first search. That's why I made couples of videos for these, so that, you know, hopefully you get it. Because it might be a point where you're being interviewed and you're given like a blank whiteboard with a, you know, marker, and you got to write something. Maybe at least remember the pseudocode. Okay, if you don't know the exact syntax, at least remember like the pseudocode of how this thing is supposed to work. That's the main thing. Okay. I know it's towards the end of the semester, so that's why for this week I'm taking it easy on you. It's just a little baby quiz, which you can take multiple times too. For more information, read chapter 13. Lafore also talks about weighted graphs in chapter 14. So if you want to see some more details in there, look at that. And then chapter 12 of Quran, or even more details if you want that. Okay, but make sure you understand these things that I showed you: the breadth first search, the depth first search, finding the path between two different nodes, and that will do the magic. Okay, so with that being said, I'm going to stop it here, post the video, and you send me your emails if you have any questions.